I'm glad you guys are not like some of my other classes. Which, to be fair, I expect of you guys as upperclassmen and in an AP class. So anyway, today is 100% a review day, right? So we have our test next class. This weekend, I wrote the test, right? So I'm making it myself this time. I'm making it based off of the big ideas, right? That list that's on Classroom. You guys should all have access to that. I reviewed it in person. That's a very big, important document. It's a very user-friendly summary of all the expectations in my giant AP binder for what you should be able to do for the end of this unit, right? I won't even read them. The AP, that they phrase learning expectations as academically as possible is a nice way to put it. That big ideas sheet is a layman's term summary of, hey, these are the big ideas that we're supposed to know. That's a very important document for all of you that I 100% recommend you review and take time to understand as a way to study and see where you're at in preparation for the test next class. All right, so I wrote the test. You guys should have done the progress check, multiple choice question A. Now, I think I checked, and I don't know if anybody did it.
I felt like there was something, but I didn't know what it was.
I checked this morning, and it was not looking good, in the sense that I don't think anybody submitted it.
Submitted what?
The progress check A. I said, hey, I'm going to have you guys do the first one on your own. The second one, I'm going to do with you now.
Are you sure?
Yep, because I said, you guys do A, I'm going to do B. And I assigned it to you all, right?
I never saw anything to do with Classroom.
No, not Classroom. It's all in the AP site. So when I assign it, it gets released there. Yeah, did nobody do it? I mean, it's ultimately not critical because, again, I didn't assign a grade to it. That was just my way of saying, hey, you guys do the first one, see how it goes. And in my head, you guys would come back right now and say, like, hey, Mr. H, we sucked at the quiz. Like, we need a lot of help. Or
that's probably everyone's answer.
Or you're like, hey, that went pretty well, except I have a couple questions on this. And I would be able to respond to how it went, things I can help with. Andre, Brody, can I get you guys to put your phones away, please? So again, it's not a huge deal, because that was 100% review for you guys. So what you guys can do is, it's still out there, it's still available, so you guys still have that as a mini practice test. Now, I almost guarantee you that will be harder than my test, right? That their AP, they're going to do very tricky wording, they're going to ask very specific things, they're going to really challenge you because that's the expectation for an AP class. So understand, if you get like 75% on that AP practice, you're sitting pretty darn good. Right? My test, I tried to be very much more focused on these key concepts that you needed to be able to do. So anyway, what we're doing today, we're going to do the second one together. I want to walk through those together so that you guys can like think about in your head. We're going to solve and you're like, holy crap, that wasn't even close to what I was thinking. Let me figure out how I should have been thinking about this question. We'll work through it together. And then I'll have time that I want to just leave as open review. We can review certain notes, certain topics. The big ideas guide we can talk through again. I desperately want your guys' questions, right? If I sit and ask, like, what questions do you have? I'm not inviting you to be silent and to pretend like you know it all. If you don't know it, let me know, right? Please, I hope it's not that you guys are prideful and you don't want to admit that you don't know things. Because then you shoot yourself in the foot for the sake of your pride. I don't care about your pride. I care about your learning and your understanding. If you don't get something, one, there's a good chance someone else doesn't. So ask the question for them. But two, give me the opportunity to help you, to give me the opportunity to clarify something that maybe I didn't clarify at first, but I can connect the dots for you guys, right? So when I get to that, please let me help you in some way, or let me at least brush up on little things. That being said, progress check. Again, there's 2 multiple choice ones. And I assigned A, right, the first set.
Want us to do that now, or?
No. A, you guys are gonna have to do that on your own time, but it's still available. It's still like a big practice test that you guys can take. What I'm gonna do, I want to do this together. I should probably unlock it. I'll unlock it just so that you have access to it afterwards, but we're going to do this together, right? I'm going to do it on the board with you guys. All classes, no timer, yes. So it'll be available for you to do. If we do this in class, you're like, crap, I want to try that again myself. Go ahead and do that. So then what I'm going to do is preview Part B. We're going to do Part B right now together as a way to practice. No, you can leave them away, right? We're literally going to all do this simultaneously on the board right here. Yep.
No.
All right, can everyone see that? Virtual student, if you're going along with us and this is hard to see, I encourage you to go in the myAP classroom and open up Part B. You can view it, and then you can do it with us or see the question up close. I can't really make this any bigger without ruining the pixelation or only seeing part of it. So what I need you guys to do is to help me figure these out, right? Again, I'm going to take this off, if that's all right with you. I'm going to stay up here. Again, you guys, if you want, make sure that you all are away. You guys can take these off since we've got 6 feet between us.
Including virtual students.
What?
Including virtual students.
Yes, virtual students, feel free to take your masks off if you'd like. First question, right? 3 blocks, string connecting each one, and you're pulling on this end string. You're pulling all 3. 3 boxes, they're pulled to the left. The strings have no mass. You need to include those in our calculations. It's a horizontal surface. M1, M2, M3 are the masses. M3 is the biggest. Let's see. I'm going to just circle this. Mass 3 is bigger than mass 2 is bigger than mass 1. No friction. Right? What we're doing now, read the question. I'm modeling you should always read the full question. No friction. And then down below, we got the force diagrams. They give that to us. They literally tell us, hey, here's the forces on each of the blocks. So you see that? Block 1, you got M1G and the normal force. Makes sense. You have the force applied pulling to the left, and you have tension pulling back. Right? This is trying to pull all the other blocks. Well, they pull back. Newton's third law. The same tension that pulls back is what is actually pulling block 2. And then you have a little bit of tension that pulls back on it. And on the very end, right, you got gravity and normal force that are balancing, and then this little tension is actually pulling block 3. Right, so that's the situation. Question is, given that M3 is bigger than M2, is bigger than M1, how did the force and the string tensions A and B compare? So compare the magnitude of the forces.
So the force is bigger than tension A, which is bigger than tension B.
Agree with that statement? That makes a lot of sense. They give you the free body diagram. When you draw a free body diagram, you need to draw the force vector, which includes both the magnitude and direction. I got my direction. It's pulling in this way. The size of my vector tells me the magnitude of the force. Well, Ethan's right. This is a bigger arrow than my tension force. This is a larger force. Tension A is a bigger arrow than tension B. So tension A is bigger than tension B. Let me see if I can... I want to check these as we go. 1, so I don't accidentally mislead you guys. And 2, so that we can... This is review. This isn't... I'm not doing a full-blown practice test. So Ethan said F is bigger than A is bigger than B. Well, that's option A. That arrow was bigger than A was bigger than B. So A is that answer. Do we all understand why that is the correct answer? Again, science, we don't really care so much about the right answer if we don't understand why. The reason why is, well, they gave us the force diagram, which is the bigger arrow, because that tells us which is the bigger force. Good. So the second question, oh, this is just a preview, it won't let me answer. Second question, same scenario, same exact instructions. It's just another question. Which of the following is the correct ranking of the normal forces? Fn1, Fn2, Fn3. Well, now all we're doing, we're going to compare the normal forces. Well, they're also given to us. The free body diagram shows us, here's Fn1, Fn2, Fn3. So, what's the largest normal force? Second largest? So the ranking of the normal forces would be C, correct? The third normal force is largest, then Fn2, then Fn1. Bingo. Now hopefully that makes sense why, right? This block 3 was the biggest mass, second biggest mass, third biggest mass. Gravity acts the same, right? G is the same, but the force is mg. Well, if I got a bigger mass, I got a bigger Fg. Therefore, the normal force bounces. Any questions about that? Yeah, pretty easy so far, correct? All we're doing is looking at free body diagrams, essentially. Again, you see up top, it's showing you these 4 questions are all linked by the same scenario. So in your head, you're like, oh, well, this is the same scenario as before. A student is trying to determine the tension in the string connecting the boxes. They want to know TA and TB. If the acceleration and pulling force are known, so A is known, F is known, which of the following pairs of equations could be used to find tension? So there's a couple ways you can do this, right? Test-taking strategy. You could evaluate the answer choices. You could say, this says MA, or M3 times A3 equals TB. And you could say, like, does that work or not? The other thing you could do is you could go back to the problem and figure out which equations and then find them matching. Again, it's totally up to you. So what are some thoughts? One thing I would recommend, this is a pretty simple diagram. So in my head, I'm thinking, I'd like to start there. Let's start simple. If I look at block 3, I know the force total, and I know acceleration of the system. Can I calculate for just block 3? How would I figure out tension B just by looking at the third block? What do I do? know the acceleration. I know the mass, don't I? I don't know this value. That's what I want to calculate. Thoughts?
Just if it was in there, right?
Newton's second law. You will use Newton's second law a shocking amount in this class. I mean, it's a fundamental law of physics. We're going to use it over and over. I can do F equals ma. What's, again, I'm only looking here. What's the mass? It's the third block. That's a known. My acceleration is known. It said, hey, your acceleration is A. You know it. It doesn't give you a number, but you know it. What forces are being applied on block 3? I got gravity, normal force, and tension B. What do I include in my, sum of the net forces? Where's my acceleration going? Acceleration is a vector. So don't I only consider the forces in the same direction? These are irrelevant. I want this. What forces do I have in this direction? Tension. TB, positive or negative? This one's tricky. Positive would be correct if we said that this is positive acceleration. If we say, oh, no, we're going to use our coordinate system like we always do.
Oh, so
In this case, this is negative and that's negative. So you need to pick and choose. Whatever coordinate system you use, you pick it and use it the whole way through. Which way do you want to do it? It doesn't matter.
just make it all positive. I like positive.
Like do it this way or this way. So we're going to say this is positive x. So then tension is positive. Well, there's our equation. The tension B is equal to M3A. Well, let's go to our... Do we see that equation anywhere? I see it right here.
The first two.
Classic multiple choice. You solved half of the question. Well, they give you two options with that. Classic multiple choice.
Roll the dice.
Hey,
Aiden lives on the edge.
Quick look.
Now, we're not going to live on the edge. We're going to figure out the other one.
Yeah, it's neither. of them.
So it's...
C.
Definitely see.
What's it between?
Heads is A.
Heads is A, then what's tails?
B.
Alright. So heads is A, tails is B. B.
It's B.
100%. All in.
In the words of Riley Fuqua, tails never fails.
That was
That is 100% statistically impossible.
Excuse me.
And false.
Prove it.
That would be so easy to prove. Flip your coin one more time. Flip it one more time.
Do it.
Fail.
Okay, one more.
No.
I want to see how much luck this is. Well, luck doesn't exist, but
This is science.
you're right. Luck.
Where is luck an element?
I don't believe luck exists.
Exactly. Tails.
It's
It's a winning quarter.
This is such a statistic improbability. Do it one more time.
We're already so low.
Do it another one.
No. Alright.
Also, y'all could be lying to me. I can't see from here. Is it really?
Yeah, furthermore.
That is unreal.
Tails.
Ugh.
Jeez.
Need I say more? You gotta say more.
This class is why a sample space is important.
Why, what?
A sample space, like statistics.
Oh, I was
Right? If I flip a coin, it's tails. It's like, oh, tails always works. You did it once. So that's my point. You've done it 4 times. Really, if you did it 100 times, you're going to see... Actually, tails technically is favored. It's like 51% tails, 49 heads, because the head side has more material, so it settles to the bottom more often. So technically, tails is a slightly better choice.
Wait, so you're telling me now?
I
Do
could also
you
do
have
both
just a
sides.
flat, round piece of metal?
Huh?
Do you say something that's flat and round? Like I'm saying, like that's not my point. Because I was thinking, what if you just put a mark on
Like a
it?
blank? Yes.
Yeah, a blank and then flipped it.
It should be 50-50.
Yeah.
Like, again, probability says that there is an equal chance that side A shows up than side B. That's why I'm saying tails never fails is garbage. Now, for whatever anomaly that it worked 4 times in a row, I couldn't explain. But anyway, we are severely off track.
Which means that B is the correct answer regardless of what you say.
We're going with B.
Because it's backed up 4 times by two
By-
signs.
Obviously.
Wait.
Oh my god! I just got it 5 times.
So dumb.
I will admit that's very impressive. Well, not impressive. Surprising.
It's got to be the way he's flipping it. It's got to
You
be.
just dropped it. And
I literally just dropped it on the ground. I was just holding on.
All right,
to it. It fell off my desk, and then it goes.
focus back up, please.
Right.
That's it.
All right, back to physics.
I thought it was physics. It fell off the table. Whoops.
All right.
Actually,
F equals ma, right? I'm doing the same thing. I know my mass. My mass is m2. I know my acceleration, right? This is my a. I know this. I just need to figure out, well, what forces cause that acceleration? Well, what forces act? Do I consider gravity or normal force?
No.
No. They're in a completely different direction. It's not just that they're in an angle. If it was an angle, I'd have to figure out the components, but it is in a perpendicular direction. My x and my y direction are independent from each other. So, if this is positive, right, this is our positive acceleration, which of these forces is positive? TA. So I got to say, hey, TA minus TB.
Oh my goodness, it's B.
It's B, right? So this
So we were
this
right.
says this force minus this,
Order.
whatever the resultant force, right, this small component of TA left over, causes this acceleration.
That's
So,
okay.
It's
B.
because it's ordered.
That's not okay.
It's
Right?
ordered. I'm telling you.
So we're going to say
It's
B,
ordered.
and it's B.
Oh
It's the quarter. Does it make sense how we solved this? Right? Newton's law. Newton's second law.
Wait, maybe it was just that quarter, okay?
All right, okay, please, put the quarter away for a
I have
second.
3 more. Hold on.
Come on.
Just all the list. I have 3 more, and then I have 2 dimes and 2 pennies.
Ooh, we got some. Okay, the 4th question. Same scenario.
Over here.
Same information.
Stonks.
We got a lot more.
Oh.
So, again, super important to read the question. We put a force probe on string A. The force probe measures, like it reads out, hey, here's the force at any given time. With box of mass 3 held in place by a student, a second student pulls to the left on the force probe, pulling on F, right? The applied on the far end. Second student pulls with a steady force, with boxes remaining at rest. So this is the readout of the force applied, right, on the very edge, and the force of tension right here in between M1 and M2. It says box M3 was held in place. Like you press that into the ground and fix it. Then what you're going to do is someone pulls on the edge, right, M1. As that student pulls with a steady forces, the boxes remain at rest, and you read out these values. That's the situation. Based on the measurements, how do the magnitudes of the 2 force quantities compare?
I think it's either B or D.
Wait. B or D?
Goodness.
Which one are you favoring, B or D? You think it's B? Alright, so heads is D, tails is B.
Oh my gosh.
Word.
Don't touch it.
Tails.
It's tails.
Is it really?
And it's all different quarter too.
Yeah. This one has the biplane on it.
So what it's tails.
Is that like the South Carolina
tails
thing or
is B.
something like that?
That's B. So it's B. I think it's B. I actually don't think it's B.
Oh my god.
The first head.
Aww.
First head. What's
There you go.
6-1.
What's 7 with a different quarter? So this quarter's defective. We can rule that out. This quarter's defective. We can rule that out.
This might take a while.
Alright.
Tails.
Tails.
A working quarter. Another tails.
Tails.
Another working
It's tails.
Tails.
All right. Focus on this question though. Option A.
quarter.
Are the quantities in agreement numerically?
No.
No.
No. That doesn't make sense at all. They are not in agreement numerically. So then the other options, they agree within experimental uncertainty, but they're not exactly the same.
Yeah, 'cause
Right?
If you round to the nearest whole number, they're the same.
Yeah. So that's a plausible option, but we need to read all the options. B or C, they disagree by an amount that's larger than experimental uncertainty. So do they vary enough to be significant? And then D is they cannot be compared because the force probes have different levels of precision.
One goes to whole numbers, the other goes to
So there's definitely different force probes, but that doesn't tell us the level of precision. So what do you guys think? Again, this is where AP, they will try to push you to the limit. Do we think that they're close enough that they're just a certain uncertainty away? Like a rounding error, basically? Are they off by enough that it's like, oh yeah, those are way different? Or do we not know? I personally would be torn between B or D.
Yeah, that's what it is.
It's frustrating because they don't.
Well, the quarter says it was B, so
It is.
AP says B.
Ooh.
The tricky thing is you don't really know this level of precision,
it was C before.
but your guys' thought was good. You were like, well, if it basically rounds, they're correct, right? The 10s are within 0.2 of each other,
Right.
and all the 11s are either a 10.6 or a 10.8. So they're within 0.2 of each other. That's consistent, so that's like, okay, there's something there. That one's really weird. That's the type of question I won't ask you on the test. All right, new question. 5 and 6 are tied together, so this scenario we're doing together. Hockey player hits a hockey puck with a stick. You got an applied force. Force applied. Right? Travels 0.85 meters while experiencing the force from the stick. It leaves the stick with 8 meters per second, constant speed, straight line along the horizontal for 12 meters. No friction. It says it's negligible. We don't care about friction. The question is, how does the magnitude of the force exerted by the stick on the puck compare to the magnitude of the force that the puck exerts on the stick? Again, they're going to confuse you with a big, long scenario. And add-
the force exerted by the puck, or by the stick on the puck. But the puck is the one used.
Okay.
What's the two possible answers?
I will give you a hint. Remember, what are Newton's 3 laws? Yeah. That's the first one. It's going to stay there unless a force acts. Well, it's moving. We got a force acting.
Oh, wait,
That doesn't really help us. Second law, F equals ma. We could do that. What's his third law?
Every action is an equal opposite reaction. So they're equal.
Yeah.
Oh.
Newton's third law. When I apply a force on an object, that object applies that force back on me. Right?
So the head's at C, tail's at D.
No, this shouldn't be a luck thing.
Just C.
There's a scientifically correct answer. What do we think?
Josh.
Stop with the quarters,
It's
please.
a dime.
Oh my gosh.
Luckily, it landed on heads, which I declared as C's, and the answer is C.
What do we think the answer is?
C. Dime is
Do we all agree?
Well, before the dime was
Do we understand
Yeah,
why? If my hockey stick hits the puck applies the same force back. Equal and opposite reactions, yes. So, we want C. C. Whatever force I'm applying on that puck, the puck also applies on the stick. Right? That's why you can't kick a ball without it hurting your foot a little bit.
Unless you're Andre.
Alright, think of a bowling ball. You can kick a bowling ball, you apply a force on it, but the bowling ball applies a force on you too. Yes. Newton's third law. Every action, there's an equal and opposite reaction.
Except the bowling ball doesn't get broken.
So this one, same question. Which of the following best describes the force or forces exerted on the puck after it's hit by the stick and slides on the ice?
It's D.
I want to explicitly point your direction to after it's hit by the stick and slides on the ice. AP will very much trick you by asking you very specific things. This question it does not care about when it hits the puck. As soon as they're done in contact, that's what they're asking their question about. And it very much will change your answer. So notice, it goes while experiencing the force from the stick, the puck leaves the stick. This is what we want. The puck leaves the stick with a speed of 8 meters per second, travels at constant speed in a straight line along the horizontal ice for 12 meters. Friction is negligible. Now it's asking, what forces act on the puck after it leaves the hockey stick? Which option do you like? The applied force from the stick is still exerted on the puck?
I think it's D.
I got a B. Since the puck's acceleration is 0, there's no forces exerted on the puck. I heard a D.
Yeah.
No force exerted on the puck. Gravitational force and normal force are exerted on the puck and are equal in magnitude. C was saying no friction, no normal force, but gravitational force is exerted.
Definitely not.
Can we cross out A?
Yeah.
A is a completely different scenario than what it's asking.
Josh. I'm taking all of them and going to the trash.
Now B, it says there are no forces applied on this object. Is that true?
No.
Why isn't it true? Give me one reason why it's not true. Huh? After the puck leaves. So hockey stick's out of play. If you say that this is not true, that means there has to be some force acting on the puck. Give me an example so that we can confirm that this is not true. Maggie's got it. What'd you say, Maggie? Gravity. That puck's sliding on the ice, the hockey stick's not touching it, gravity still acts. What also acts?
Friction. No.
No, friction's negligible. The question excluded that.
Natural force.
Normal force. It's all right. So this is not true. Because Maggie said, hey, gravity acts on it, therefore this is an incorrect answer. This is saying normal force is not exerted on the puck, but gravity force is. What would be happening if this were true? If you had no normal force, but a gravity force? What would the puck be doing? Going down. It'd be going to the center of the earth. So this is not true. Yep. Now, read D and confirm that it makes sense. There's no friction. Correct. Problem said there isn't any. The gravitational force, like Maggie said, that's always acting. And a normal force are exerted, and they're equal. Well, that's true. That's what normal forces do. Whatever surface it's on, it opposes the gravity force. So D is the only option that still makes sense. Bam. Does that make sense? Do we get that thought process? Right? This is a great question where you just evaluate each option. You could read choice A and say, this is a stupid answer. It just said what force is acting after the puck leaves the stick. Well, the stick's not in the picture, so I wipe that one out, right? Process of elimination, that's a good test-taking strategy. Good. All right, I'll try to... Ooh, does this look familiar?
Yeah.
Yeah. Oh, good. Nice. Sorry. I didn't intend that to be there. There, a little simpler. Motorized cart with a string over a pulley. You got a block hanging on the other end. The cart is accelerating to the right. Which of the following best represents the forces on the cart as it's, accelerating? So we got some options. This one looks okay. We're talking about the cart. Is there any we can get rid of? There's a couple we can get rid of right away. You sure? There's two of them that are obviously wrong. B and D. Why? Normal force. It's all right. You guys are saying normal B and D? If B and D were true, this cart would be flying up in the air.
Yeah.
Because I have more normal force than I do gravity. What? It could be. Wasn't in the problem, though. So in this case, B and D are out. This is totally not matching the situation described. So then I got to look at A and C. Well, the normal force, gravity, they're equal opposite in both, so that's fine. Now we need to check.
What A and B, C? Because if the cart's able to move, wouldn't that mean that the applied force is greater?
Yes. Aiden had very good reasoning. It said it's accelerating to the right. In order for this cart to accelerate to the right, where does the net force have to be? To the right. Your net force and acceleration have to be in the same direction. And Aiden said, well, this can't be the case, because that would mean there is some net force to the left. Well, then the block would be pulling the cart off the table. And said, no, this is correct. There's more applied force than tension. The leftover is allowing it to accelerate to the right. C. There we go. Make sense? You're using free body diagram and you're understanding of Newton's second law that whatever the net force is, the remaining force, that direction is where the acceleration happens. Good. Ooh, got a ramp. Block slides, constant velocity. What does the word rough mean? Friction. Rough is that trigger word for, hey, friction's involved. There's an angle theta with the horizontal. Experiences three forces: gravity, normal force perpendicular to the surface, and then friction along the surface. Which of the following gives the magnitude of the net force on the block? What do we think? Yes, you can.
Josh, check the quarter.
No, quarter will be between. We don't know yet.
No, don't do the quarter, please.
How about the penny?
We need to get the forces along the surface and perpendicular to the surface. What do you know will be true about perpendicular to the surface? Will we have an imbalanced force in this direction? Do we have motion in this direction? No. Can someone see the ultimate shortcut in this question? This question, you don't actually have to do anything.
Isn't it?
You can't say that they're equal because they're different directions. But the component of gravity pushing into the ramp is equal to normal force. We know that because it's not moving in and out of the ramp. It's sliding down the block. Did you guys, anybody catch this?
Constant. There's no acceleration.
No acceleration.
Yeah.
If there's no acceleration,
Oh, the net force is 0. Oh, I'm dumb. Net force is 0.
oh, ultimate hack.
So it's A.
It's A, 0. AP will try to trick you. They're going to force you to read the question carefully. Hope I'm not wrong. Boom, good. Do you understand why this is correct? My two directions are this way and this way. This is where my motion happens. Well, this way, Maggie was right. The normal force and the part of gravity pushing down, they're going to balance. My block's not going in and out of the plane. It's staying level with it. My motion is in this direction. If my object's at a constant velocity, there's no acceleration. If there's no acceleration, there's no net force. I don't even need to do math. I just say, like, there's no net force acting on this object. Boom. All right, Atwood's machine. Two blocks have an equal mass. They're just about to slip. So there's not motion yet. Also, there's a free body diagram for the block on top of the table. The coefficient of static friction between the table and a block resting on it must be... Ooh, this is a good one. How are we going to do this one? Can we get rid of an answer right away? 0. Option A can't be possible. If you have 0 static coefficient of static friction, that means you have no friction. That's not the case.
Between 0.5 and 1.
It's a good question.
Because it's not moving yet, but it's very close to moving.
Yep, it's in static, right? There's no motion.
So wouldn't 1 be is right?
Well, we can look at if there is no motion, don't these two have to be equal and opposite?
Yeah.
What tension force is being applied?
In is the mass of N.
You have this is where they're gonna the Atwood's machine. You can't just say the tension is gravity, because if no, you can. We're not in motion. Everything's stuck here. If this is not in motion, gravity equals tension. So in this case, you could do, right? My tension force comes from the force of gravity pulling this down, and tension directly opposes it. There's no motion yet, so that will work. Friction. What's my equation for friction? You remember what that letter's called? Mu. Right? This coefficient times normal force. What's the normal force equal to?
Gravity.
Of this block, it's equal to gravitational force, which is mg.
And they're equal.
So what's mu s have to be?
Zero.
This is an equality.
One.
1. I'm almost positive that that's correct.
And the gauge is
Oh, yes. Good. I missed the question. So that's a tricky one. Ethan knew that the tension was gravity because it's not in motion. It's balanced. Gravity and the tension are balanced. The normal force, the friction on the block on the table, normal force is equal to gravitational force. Well, it's the same mass block. So this mg, this has to be at least 1, right? This could be like 20 because it's static friction. It'll apply whatever you need up until the limit. So that's why the answer is at least 1. Good. We're getting there. 3 blocks attached by strings. Coefficient of friction is mu. Tension on the left and right strings is T2, T1. The acceleration's A. What is an expression to say what T2 equals? This guy. This one's tricky. We got that, don't we? It's asking, well, what's T2 equal to? What did I miss? I missed the friction force. The challenge is they wrote this in terms of T1.
Yeah.
So I got to go over here and figure out, I got FG2, FN2. This is T1. This is T2. These are equal opposite. I'm not drawing them to scale right now. I'm just scratching out my ideas. This is something I can use. I want to say F equals MA. My mass of this object, M2, right, times A. I know that. It's given. What are my forces acting on that object in this direction?
T1.
Positive T1, right? Minus, oh, what else did I forget? Forgot friction.
I wasn't sure if that was included in the illustration.
Minus T2 minus force of friction. Well, I want to know what T2 is, so I'm going to just say, I'm going to put T2 on the other side and say T1 minus FF minus M2A. I flip these. Negative, that becomes a positive. This is my answer. Which one does it match? Well, it's not this one, right? Because my acceleration, MA, is positive. That's not true. MA is positive. That's not true. We can write F, friction, right?
Yeah.
What's the force of friction on that block? Isn't it mu Fn?
Yeah.
So I got mu times, what's the normal force equal to?
Gravity.
Which is M2G.
Yes.
Minus M2A equals T2. What option does that answer?
B.
Make sense? That one you'd start here and you have realized like crap, that doesn't give me enough info. The options are all in terms of T1. Well, then I got to draw another picture. B. Good. We're killing it so far. Did I do that? We're on question 11?
Yeah.
Oh, yeah. It looked like it skipped to a new page. Skydiver opens the parachute. A little bit later, the weight of the skydiver parachute system and the drag force are equal. Drag is air resistance. Most of the time we ignore air resistance, but when you pull open a parachute, you get a lot of drag, and that's what slows you down, right? Drag slows down gravity. So it says, hey, they're equal. The drag force and your weight are equal. What's true about the motion of that skydiver at that point? You're falling, you open that parachute, and after a little bit, the drag and your weight are equal. Well, what about your motion?
If they become equal, then your net force is 0. So you'd stay moving, but you wouldn't change speed.
Constant speed, which option's that?
B.
B. This one makes no sense. You don't stop moving the moment your parachute applies a good enough drag. You'd get stuck in the middle of air and never be able to move.
What did you also
You could get
die
that
from that?
Probably.
Yeah.
Yeah. We might talk about impulse.
Yeah.
The time at which a force is applied.
When you open it up, wouldn't it just be like it would be like impacting the ground because you just stop?
Yeah. You would. It would.
You'd be splat.
You basically go from minus 100 mile an hour
Terminal velocity
to 0 in maybe a second. I mean, brutal.
Survivable.
We're going to talk about impulse. This one, skydiver is moving down with an upward acceleration.
Yep.
That don't make sense. If that's true, then eventually you're going to start moving up. That's baloney. If you can figure that out, you'd be a billionaire. Skydiver is moving down with a downward acceleration. Well, it just said the drag and the weight are equal. They're opposite direction. They sum to 0, so that one's not true.
C and D are
So-
moving with acceleration.
Yes, so B is correct, right? They're moving downwards still, but it's at a constant speed. They've stopped accelerating. There's no net force. This situation, this is terminal velocity. Have you ever heard that phrase? Terminal velocity is the maximum velocity you can achieve because eventually the drag on your object, the air resistance, equals out your weight. And so you're stuck at that speed. So when you fall, you don't accelerate indefinitely. You reach terminal velocity. So 11B, good. Following figures show vectors representing the forces on an object which is initially at rest. In which case would the object remain at rest? We're going to go one by one. You're going to tell me the answer to all of these. Am I going to remain at rest?
Nope, you're moving up.
I'm moving up.
Somehow moving.
These are equal opposite. Nothing happens in this direction, but I have a net force, so this object will move up. That doesn't remain at rest, so that option's out. B.
Moving this way.
Yeah. Huge force over here, a little bit, right? If I take this and subtract it out, this is my new force. That's still a force, still going to cause an acceleration. That ain't at rest. Whoo!
Very scary, but it doesn't matter because the x directions are already right.
Just no. Just no.
This one's tricky.
It's just no.
The thing you want to remember is I want everything in x and y. I only got the two directions.
So you have
This
to
needs
add-
to be split into
no.
some x
Oh, wait.
and some y. Once I split that up, this needs to be added here. This needs to be added here. Well, when I look at that, that's looking pretty close to everything being equal. Because I got little guy plus little guy. That's pretty close, right? You're just ballparking this. This guy, they're about equal. I don't know if I can, something like that. That's pretty close. Let's hold that one for a second.
No. No.
What's happening?
No.
No motion or motion?
Oh, good.
Um,
Motion.
This needs to be split into,
oh, because that one also says there's a lot of. It's like double. Yeah. Yes, it's.
Pretty sure.
Yeah,
what I'm doing here, I'm resolving that force, saying instead of looking at the actual force, I'm going to break it into two pieces. These are the pieces. Well, these guys are equal and opposite,
It's not moving up or down.
but now I got two of these. Well, one of them is basically the same as the other side. So if this was F, this is 2F. So this sucker's going this way.
Right. Now.
So,
For some reason, I see the scene from Fast and Furious.
Oh my goodness.
that's where you want to look at all your options. Say, like, we felt okay about this, wasn't 100% sure, it was really close. Well, the other one was not even close. So we're going to say the object that remains at rest after all these forces get applied is C. Bingo. Does that make sense why?
Yes.
Think about when you have a force at an angle, you got to break it into x and y pieces and then add all those up. Because we want to only know the x and y direction. Good. Okay, looks like they kick a ball with force F naught. This is the ball's position at various times. What's the net force on the ball and its acceleration at the highest point? This is the apex. At this point in time, what's the net force and net force and acceleration? Well, draw me what forces are acting.
Up and, or no, up, just down.
I got FG, don't I?
There's no normal force kind of right. It's not on the ground.
Yeah, there's no normal force. It's not on a surface to support it. Do I have the F naught, the force that I kicked it?
No, because that only way.
Yeah, F naught was right here. After this, it's just in parabolic motion. So my options, is there a zero force applied? No. So you're like, eh. We can rule these ones out, can't we? We just said the kick force only happened at the kick. You don't keep applying that at the middle of the air. Well, at least that's an easy...
Also, D said the acceleration was greater than gravity.
Yeah, that's not possible. This should make sense, right? The only force is gravity. Well, gravity's magnitude is mg. And lo and behold, it accelerates at g. So we got B, right? Bingo. Killing it. Outer space. Identical mass connected by a cable. We don't care about its mass. They're initially at rest, so they're not moving. Astronaut Y pulls the cable towards her with a considerable force. Which of the following describes the direction of the velocity of the center of mass? So we didn't talk a ton about this.
So they're both gonna just
Okay, I'm going to give you guys a crash course. Center of mass I didn't touch on as much as I should have. What's our system? It said the center of mass of the two astronauts. Remember our system? What's our group? What's the object? Huh? It said the center of mass of both astronauts. Well, isn't the center of their mass right here? This is this system.
But they're in space.
They're in space.
So isn't there like no mass in space?
There's mass. You still have matter. There's no gravity. They're just floating. They're not moving at all. Remember like the horse cart analogy that we did? Remember the horse pulls on the cart and the cart pulls back. What happens if I look at the horse cart together? Do I care what happens? No. So if she pulls on astronaut X, do I care what's happening? No. They're floating together as a joint system. There's no net force on this system. There's no gravity. Nothing's pushing or pulling them. She's pulling on her or him. It's happening within the system. I don't care what happens in the system.
Well, then who would be moving if you pull on one?
they're both moving.
They're
but
both
their center
moving
of
at
mass-
the same time.
Yeah.
Yes. Remember? Newton's third law, equal and opposite. However hard she pulls back. Right? And
Are both their weights the same or does it not?
yes, they're equal. It said identical mass, which is important to note.
Okay.
When they pull, all they're going to do is going to come together towards this center of mass. There's nothing affecting the system. So it's not really going to move. The system is going to get smaller, but that's it.
Would their masses matter if they're floating in space? Like, would it,
No, it matters that they're identical. And we haven't talked about why.
like, what if one was
No, actually we did.
What if one was like twice the mass of the other?
Yeah, then
If this is 2m, and this is just m, and they both apply force F, who accelerates more?
M.
Oh, this, yeah, m. So the identical mass is a key, but the center of that mass does not move. Bam. That was a little tricky. All right, I'm trying to get you guys through this. Two blocks, 2 and 3 kilogram respectively. There's a light string, aka we don't care about the mass. The pulley has negligible mass and friction. We don't care about it. You release this whole thing from rest. What describes the velocity of the 2 block system's center of mass?
their center of mass.
Not really. The center of mass is like whatever part is in the middle, but you see how this is heavier? So the mass is like shifted towards being here. These are tricky. Again, I didn't spend as much time on the center of mass as I should have. Which direction is this pulley going to fall?
3 kilograms.
This is going to go down, right? So it's somewhere here. If this goes down to, say, here, this is going to go up, isn't it? Where's their center of mass? Where's the midpoint? I got to go a little bit down, don't I?
Yeah.
So isn't the center of mass going down? We think C, don't we? They're weird. The center of mass moves down, and the thing's accelerating, so it's going to start speeding up. Man, they put a lot on center of mass for this one. I want to skip to ooh, this is a good one. The conceptual center of mass. You drop an object, downward force on the object. What happens to the center of mass of that system as the object falls down? Think about it this way. If I have the Earth and an object, Earth applies Fg on the object, and it starts moving because nothing's resisting it. What does Newton's third law say?
It's also pushing G back.
There's also a force acting on the Earth. Remember I told you that?
Yeah.
I exert gravity on things, including the Earth. So if this is my system, and they're applying a force on each other, does my center of mass move?
Wouldn't it move towards the Earth?
Huh?
Wouldn't it move towards the Earth? Wouldn't it be like ever so slightly above the Earth and then move towards
To start with, say the center of center of gravity is here.
Right.
I have a force on an object, so it moves down to be here. Don't I have a force on an object here? It also moves.
Oh, okay, yeah.
By like
yeah.
this
Okay.
much.
I got you.
But the light mass moves a lot. The Earth moves hardly at all. Well, the force was internal.
Yeah.
Nothing's acting on my system.
Oh, okay.
There's no net force on my system, so my system doesn't really move. So, it should be C. It doesn't move. Right? Your system is important. It said the Earth object system. Well, draw a circle around that. Nothing's acting on it. It's not going to change. Everything's internal. I'm going to hustle through these. I want to give some free time. Oh, boy. Yeah, see, they're going to get tricky. They're going to add the distance in there. Do you want to keep doing some of these, or do you want me to open it up?
Let's just try this one.
Try this one? Okay. Block A has mass 4m. It's attached to block 2m, right? So this has twice the mass of this block. Negligible friction, negligible mass. So we just look at the mass of these two. It's held a distance h above the ground and released from rest. A block A reaches the ground 2 seconds later. What's the value of h? Oh, crap. What do we do?
Quarter.
Yes.
This is one where I'm almost positive you need your equation sheet, which again, you will be able to use on any test. Including the AP test. You'll get this equation sheet, right? It'll be in the back of your book, or the back of your test. Huh? What's that? It might be. Like in your workbook, it's an appendix, so it's at the end. But so I'm going to help you. I'm looking at this and I see there's an equation that says this could be helpful.
Mm-hmm.
This starting minus the ending distance, if I do y minus y naught, right, if I move it at the other side, this is final position minus initial. That's just h. So I'm going to say this is h equals, that's 0. I started with no velocity. So then all I have is 1/2 a y t squared. T squared was 2. Remember that? It said it occurred in 2 seconds. Oof, I'm really close. All I need is the acceleration of my system. Now, I'll give you a hint. Why is it not 9.8?
Because the other blocks.
This is mg. Fmg equals 4m times g. But I have tension.
Yeah.
What's tension? Right? So if I combine these, what's my net force? 2mg, isn't it? Well, that force is all that's acting on my block, so that's equal to ma, where m is 4m. Well, if this is what I want to know, wouldn't I just take 2mg divided by 4m equals ay, so that ay equals 1/2 g?
So it's
Is this right, though? So this is right, because we've looked only here, and we've drawn all the forces acting on it, including this tension, and we look at how this accelerates. So if this is ay, I'm going to plug that in here. 1/2 g 2 squared. Well, g we'll call 10. We're going to round up, so this is 5. 5 times 1/2 is 2.5. What's 2 squared? What's that approximately? 8? No, 10.
4 times 2 is
It's 10.
8.
Yeah. 10. So which one are we closest to? Because we rounded.
13 points.
But I think we go down. It's B. The reason is we rounded up.
So we have to run back up. Yeah. But
Right? Let me. Does someone have a calculator? I want 9.8 times 1/2 should be 4.5
9.8,
times 0.5
yeah,
times 0.5
times 0.5
times 4.
times 9.8.
9.8?
Yeah.
You said 9.8 times 0.5 times 0.5 times 4, right?
Yes.
Because
9.8.
0.5 times 0.5 times 4 is 1.
Times 0.5
Okay.
times 0.5.
Because half
Times
times
4.
half is a 4, and 1 times 4 is 1.
Good ring.
Is it because you need acceleration in meters per second?
That's what I'm missing. Oh, wait.
Because they gave you 2 seconds.
How about this? Do 9.8 divided by 3 times a half times 4.
9.8 times
3, or divided by 3,
9.8 divided by 3.
6.533.
times a half times 4. What is it?
6.533.
Dang it. I made a mistake again.
Good job.
6 point something.
Oh, because
6.53.
you have to add the gravity because gravity's still acting on the two.
No, I messed up the mass.
Yeah. Right, 'cause that's 4M and 2M.
Yes, I thought you said add the gravity.
You did say that.
Did you mean like add the total mass?
Yeah.
Yes. This isn't moving independently.
Right.
You have to move both objects with one force.
That's why 6.
So that was my mistake that I made. I assumed that the force applied only moves this object. Well, they're both moved together. So whatever force is left over has to move both of them. Thank you for calculating that. That makes sense? That was a good one, right? Because 1, you saw me make another mistake. Don't make that mistake again. And 2, again, these get tricky. You wanted to see me make a mistake?
No, I wanted to see.
Okay. Yeah, this was a good problem. All right, we got like what, 5 minutes? Okay. Well,
We leave right now.
be honest. Was this valuable?
Oh, yeah.
Okay. Okay. It took longer than I thought, so that made me nervous that I was not getting through stuff as quickly.
Test is canceled.
But no, I'm glad this was valuable, right? Right. So again, AP level. Some of this stuff we know these concepts. We got them. Questions like this, yeah, they're tricky.
Am I allowed to
I
use a quarter
vote
on the
we
test?
all have a quarter when the next test comes out. We all get a quarter.
You all want
We
a
all get
stupid
We all
quarter.
get a quarter for the AP test.
One thing I want to point out. Bring this. You guys should all have this. You should all just like always leave it in you. You will be able to use this. So a problem like this, you'd be like, holy crap, how do I get the acceleration? Well, what equation has the acceleration in the variables that you got? Turned out really easy. And then I could go back to Newton's second law, not make the mistake that Mr. H did, figure it out, and boom. Again, your test will not be that hard. Do you guys, I made the test as a Google form. So virtual students, you guys are going to take this virtually. You guys are going to have to, I don't have a proctoring service, so this is going to have to be your guys' integrity that you're not just sitting on your notes looking up answers. But for you guys in person, they're going to take it virtually as a Google form. You guys, I can give the option to do either, but I would prefer it if you did it in paper. Do you want me to print it out, right, and you just do it like a normal test? Okay, I'll print it out. It'll be there, and then I'll just give you a sheet of paper, and you can take it like a normal test. It's, I think, 30 questions, but a lot of them are easy.
Did you find these?
You want me to show you one of them?
So something I noticed is that dimes so far are more likely to land on heads than quarters.
Do this one with me. Weight is a measure of mass and is measured in kilograms. True or false?
Weight is measured in measured in kilograms.
False.
Is that true or false?
I don't even know. I think it's false.
Yes, you do.
Oh, it is.
Do we say something weighs 10 kilograms?
Weight is a measure of
I mean,
Force
we
of
do,
gravity?
but we're not supposed to.
Yes. Yes, yeah, we say it incorrectly.
Yeah, that's what- okay.
Yeah, so true.
Mass is kilograms. Weight is completely different. This is false. Object traveling at a constant velocity of 15 meters per second is experiencing no net force. True or false? True. Constant velocity. There is no acceleration on the object. No net force. True. Last one. I can't give away any more. This is literally a test question. Like, this is on the test. The measure of how much matter an object has is called, typo, mass. We measure mass in kilograms. True or false?
True.
True.
So I just gotta remember false, true, and I'll get 3 out of 30 questions right.
At least.
I think it'll scramble your questions.
Okay, well I just gotta remember those 3 questions, and I'll get 3 out of 30 correct.
There you go. So again, the first half.
Easy 10%.
Let me fix my silly typo.
Tails.
Anyway,
All coins are 3 sets of tails.
You're trying to tell me that if you were to go every single day, the first time it is ever supposed to be
there's like 18 true false and 12 like actual like do some math. It's fine. Please study, do the multiple choice progress checks if you want practice. You can redo this one. Test is next class. I forget what else I'm supposed to say. We'll likely start the next unit, but like just the topic of it.
Oh, well.
How do you feel about it?
I feel good.
Good?
Yeah.
I was a little more prepared as a teacher for this time than the first unit, not knowing what I was doing. And making the test myself is going to be
A lot better.
a better like stepping stone to do the like AP is still AP. Like I can't change that, but we can at least take baby steps. And then when we review for the AP test, you'll get like full blown practice tests. And
In AP Chem, that's what Cunningham did. He gave us our like unit test as AP tests and said you get what you get. And this
Ooh.
time it was like 60%. But he was like a curve and rounded up because it was so hard.
okay, dang, that's tough. Yeah, Shay.
Oh, hey, happy World Teacher Day.
What? World's Teacher Day?
Yeah, happy National Teacher Day.
Is that a thing?
Yo, you didn't think it's going to the whole classroom?